our last section, 8.3, volumes. Just as area is always positive, so is volume. So we're going to be talking about how to find the volume of shapes. Just like we might have done in geometry. To find the volume of this, we would do the area of the base times the height. Okay, same thing here, area of the base times the height, area of the base times the height. So we're talking 3 dimensions here. So if we slice this in tiny little slices all the way up, we're going to be able to find the volume of each of these. Okay, so imagine you have this graph here, and this is the area of one face, and we might have another one, you know, somewhere over here, and another one over here. If we take all of those areas and multiply it by how wide they are, that'll give us the volume of this whole thing. And so here's just a stronger example of that. All right, so the definition of volume, we have 3 dimensions here. We have an area, which is 2-dimensional, and we have the dx, which is 1-dimensional. All right, so show that the volume of a sphere is this. This is something that you should remember from geometry. All right, so if I try to sketch a sphere, make it centered at the origin, why not? Okay, you can make it look more spherical by adding these dashed lines. You don't have to, doesn't really matter. All right, we're going to make the radius r. Now, if I wanted to find the equation of this, then we know that x squared plus y squared equals r squared. If I solve this for y, I'm going to get y equals plus or minus square root of r squared minus x squared. The plus part would be up here, the minus part would be down here. All right, so if I was going to cut this up, I wanted to find an area, okay, of one piece of this. It's dx units deep. Okay, it would look kind of like a disc. Okay, so imagine I'm viewing it from the side, or a flat cylinder, disc with a C. All right, so the area of that disc or that circle is pi r squared, and the radius in this case is going to be here, which is the square root of r squared minus x squared. So if we wanted to find the volume now, we're going to have to take the integral, and if our radius is r, we'd be going from negative r to r of the area, pi times the radius squared, and dx. So we have our area, which is 2 dimensions. We have our dx, which is 1 dimension. I could pull the constant out. All right, and then that squared, we're just going to have r squared minus x squared with respect to x here. Integrating. Remember, we treat r as a constant here. All right, simplifying, let's plug this in. So we get r cubed for the first part, minus 1/3 r cubed. Okay, minus negative r cubed plus r cubed over 3, or 1/3 r cubed. Keep simplifying here, so we get r cubed plus r cubed. So we get 2r cubed minus 2/3 r cubed. All right, so 2 minus 2/3 would be 4/3. So we have pi times 4/3 r cubed. So we get 4/3 pi r cubed, which is exactly what we know the formula as. So this is where it came from. So let's look at a different example. So for anything where we can make discs or circles, anytime our cross sections are perpendicular to our axis of rotation, we can use these discs. Okay, so we can use this volume formula. All right, and a way for you to remember that is if the region is perpendicular to the axis of rotation. All right, so here's your example. We have the x-axis, y equals x squared, or square root of x, and x equals 1. So this is our region here, and we're going to rotate it about the x-axis. All right, so it might look something kind of like this, where we'd have all these disks. So to find the radius would be the top minus the bottom. So it would be square root of x minus 0. All right, or just square root of x. Our width is dx. So our volume is simply going to be pi times the radius squared. And in this case, we're going from x equals 0 to x equals 1. Okay, so pi times, and that's just x. So when we integrate, we get 1/2 x squared. Going from 0 to 1. Pi times 1/2 minus 0, or 1/2 pi. Okay, so the key word for these is perpendicular. Example 3 is similar. It's just this time, instead of rotating this region about the x-axis, now we're going to rotate it about y equals 1. Okay, so now we have maybe like this cornucopia shape here. So the disks are going to be along this shape. All right, so our radius this time, if I was going to draw this, now it would be 1 minus x squared. That would be my radius, r of x. Okay, my width would be dx. So r of x is 1 minus square root of x. Find the volume. All right, pi times the integral of the radius squared, 1 minus square root of x. Quantity squared dx, and this time we're going from 0 to 1 again. Pi times. It'd probably be easiest to distribute that out. 1 minus 2x to the 1/2 plus x. All right, and I would like you guys to finish this problem and write your answer in simplest form for your whisk. Okay, so find the volume, put it in your whisk. And then our last example uses an idea that we covered in the last section. This time we have y equals x cubed, which is going to look something like this. Y equals 8, somewhere up here, and x equals 0. So we're talking about this region. And we're going to rotate it about the y-axis. Okay, so this time we're going to rotate it this way. So we're going to have this kind of shape where these are our disks. So the width, instead of being dx, is now dy. So our functions need to be in terms of y. So this will be the cube root of y equals x. That would be solving. All right, and then so that'll help us find our radius. It's going to be from this line all the way to 0. So our radius is cube root of y minus 0, or just the cube root of y. The volume is going to be given by pi times the integral of the radius squared dy this time. And now our bounds need to be y values. So we're going from y equals 0 to y equals 8. Volume equals pi times the integral. So this would be y to the 2/3 dy. Add 1 to the power, we get 5/3. Divide by that new power, 3/5. We have pi as our constant here. 8, 0. I could pull that 3/5 out. Okay, so 8 to the 5/3 minus 0 to the 5/3. 8 to the 5/3. The cube root of 8 is 2. 2 to the 5th is 32. So we have 3/5 pi times 32, or 96 pi fifths. So we're going to talk about a couple different other methods on the next video. But the big idea of today is, I want to go back to this. If our cross sections are perpendicular to the axis of rotation, I want you to remember the perpendicular method.